Please add these two functions to your arsenal of functions. You have a big arsenal of functions now. Polynomial, linear, quadratic, rational, absolute value, radical. So we're adding now the exponential function a to x with a base greater than 1 and its inverse function log base a of x. These are inverses of each other. Now, when the base is between 0 and 1, we have a different scenario. This is a to x when the base is between 0 and 1. And this is log base a of x with base less than 1, between 0 and 1. So please add these two functions to your arsenal. And of course, please remember every time I graph the function and its inverse, I should always graph. It has to go through this point. Or I should always graph y equals x. Always. To make sure that I graph them symmetric with respect to that line. What else we learned last time? We also learned super important. Log base a of x is y is the same back and forth with a raised to y equals x. Another super important is the change of base formula. Log base a of x is the same with log x over log a or natural log x over natural log a. These are the most important topics from last time. And now I would like to practice. I hope you have a multimedia library, so
what page are we supposed to be?
Yes, I am just now opening it. I'll tell you in a second. I went directly to 4.3 and I'm going backwards because it's easier to get to problem set in 4.2. Yes, I'll give you in 1 second. This device is slow. Sorry for the wait, a second. Okay, 490. 490. 490 and 491. Okay, I would like us to look at a transformation. So, for example, problem 66. Feel free to choose any time. I'll give you time for a second after we finish this to choose. In this problem, we are asked to use transformations to graph g of x equals natural log of x plus 1. First thing I would like to refresh your memory on, and maybe I should write it up here because it's in the same realm of what we're doing. The exponential function has domain all real numbers. We like to write this, and a range 0 to infinity. You don't have to write that double R bar, so this is negative infinity to infinity. But what happens here with the log function, is, as you see, the domain of the log function is 0 to infinity. 0 to infinity, but the range is everything. So the log is defined on 0 to infinity and taking values in the all real numbers. So every time I see a log, if it's natural log or common log, any log, I have to write the restriction that x plus 1 must be a number greater than 0, not even equal to 0. So then from here, I know that x must be greater than -1, and domain is -1 to infinity. So I know what to expect. So when I use transformations, can anyone tell us what was the base function for this? Which function did we use to determine this? The base function is natural log x, which we know the base is greater than 1. Here it is, base greater than 1. This is the shape. Okay. As you see, it has a vertical asymptote x equals 0. Now, we already determined the domain. We know exactly where this function will go. Where will it go so I can graph natural log of x plus 1? So that's only one transformation, a natural log of x plus 1. Where does it go? We shouldn't need to think because I already see the domain. So this is obviously a shift of 1 unit to the left. 1 left. But I have to shift the vertical asymptote first. How many units? 1. So the vertical asymptote is now at -1. And I'm shifting this graph 1 unit to the left. Here it is. So this is natural log of x plus 1. And this one was natural log x. Do we need more transformations or can we look at more domain? Exercises 109 through 112.
We can do domain now.
Okay, very good. We can go back to other problems. Okay, so can we choose? Anyone would like to choose 109 to 112 on page 490? If not, I will.
111.
111. And we have f of x equals common log. I don't see a base. If I don't see a base, it must be, and it's written log, the base is 10, of x plus 1 over x minus 5. Just a few minutes ago, we said that whatever log I have, it doesn't matter. This quantity has to be positive. Well, this time, this quantity has to be positive because log is applied to it. So then I have to write x plus 1 over x plus 5 has to be greater than 0. And now this is your first application of what we studied in the previous chapter when we looked at rational inequalities. And I showed you that table, which some of you did not use, which is fine. You used a different method, that's fine. It's a ratio and 0 on the other side. So x is the variable in the problem, x plus 1, x plus 5, and the ratio. Which numbers go in the table? Only one for each factor. Which number I need for x plus 1 and which number I need for x plus 5? Anyone?
-1 and -5.
Excellent. In this particular order. Great job. For x plus 1, I have a 0. For x plus 5, I have a 0. Now the question is, what do I have here and what do I have here for the ratio? Sorry. So when the denominator is 0, what do I have? When the numerator is 0. These are both linear functions with a positive slope from negative to positive. When I divide two negatives, when I divide a negative, when I divide no negatives. Positive, which means this and this. So therefore, the domain of this function is negative infinity to negative 5, not negative 5, union negative 1 infinity, not negative 1. Why? Because there is no equal symbol. It cannot be. This quantity has to be strictly greater than 0. Otherwise, log does not exist. Okay, so these are more involved problems. Let's look also at an example from 75 to 80. An easier situation. Can anyone choose between 75 and 80? Okay, I will choose 78, and which we have f of x equals common log again of 7 minus x. This is a much easier situation. I only have to write that 7 minus x must be greater than 0. And then I have negative x greater than negative 7. I divide or multiply by negative 1. And I get that x is less than 7. Much easier. Domain negative infinity to 7. Okay. Moving on. I'd like to look at a word problem here before we move on to 4.3. Okay. Students in psychology class, problem 119 on page 491. Next page. Any questions from me here? Anyone? Okay. Student in a psychology class took a final examination as part of an experiment. As part of an experiment to see how much of the course content they remembered over time. They took equivalent forms of the exam in monthly intervals thereafter. The average score for the group, average score, is given by the function f of t equals 88 minus 15 natural log t plus 1 for t between 0 months and 12 months. Part A. What was the average score on the original exam? Part B. What was the average score after 2 months, 4 months, 6 months, 8 months, 10 months, and 1 year? So 2, 4, 6, 8, 10, and 12. And then sketch the graph. Describe the graph, what the graph indicates in terms of the material retained by the students. So the first question, it says, or it reads, what was the average score on the original exam? What does that mean? What are we asked to determine? The average score on the original exam. When we talk about original, what do we have in mind for T? Also called initial. Both are interchangeable in this situation. On the initial exam or the original exam, what are we really asked to do? Anyone would like to give it a try? Well, the original means t equals 0. 0 months, that's the original exam. What we're going to do, we're going to plug, I'm not going to repeat this step several times, 1, 2, 3, 4, 5, 6, 7 times. I'm just going to punch in this function in the graphing calculator, and let's do that. In y equals, clear if you have anything else, 88 minus 15 natural log, in parentheses, x plus 1. Now I go to second in table. Okay. So I was just making sure that I have the independent variable in ask mode. And I'm going to plug in 0, 2, 4, 6, 8, 10, 12. 0, 2, 4, 6, 8, 10, 12. And I'm going to copy. I'm going to copy them in a table because I have to graph the function afterwards. For 0, of course, 88. For 2, 71.5. For 4, 63.9. For 6, 58.8. For 8, 55. For 10, 52. And for 12, roughly 50. Can anyone describe the pattern before we graph it?
Descending.
Right. Right. Thank you. So as I see, the height is 88, 20, 40, 60, 80, 100. 2, 4, 6, 8, 10, 12. Okay. So for 0 is 88. For 2 is 71. For 4 is 63. For 6 is 58. 2, 4, 6, 58. For 8 is 55. For 10 is 52 and 50. Here's the graph. So this is f of t. This is t. It's a decreasing trend. In 12 months, it turned out that the students remember only about 50% of the original knowledge that they had.